Good afternoon, sir.
Good afternoon, sir. I think participants are joining, so we can wait for some more time. Then we'll start.
Yes, sir. We'll join for let's join for 5 minutes. Let's wait for 5 minutes. We'll join.
Yes. Okay.
Okay, let's start this session 4. Today is the end of this 2 days workshop and hands-on training program. Dear participants, respected speaker, a very good afternoon to all of you. And today we have with us Mr. Kaibalya Prasad Panda, Research Associate, National Institute of Technology, Meghalaya with us. Sir has already delivered a lecture over the fundamentals of photovoltaic cells, MPPT design, its corresponding tracking methods, microgrid design, the penetration of electric vehicle to it. Then sir has already talked about multi-level inverters, reduced order multi-level inverters, and the reduced switch multi-level inverter as well. So let's discuss all of those and just try to implement them in MATLAB in this hands-on training session. It will be really nice if you try that by yourself along with for your preparation and re-improvement as well. So let's invite Mr. Kaibala Prasad Panda. Sir, please go ahead with this. And it's basically a hands-on training session. So it will be really better if you practice it. Just while there might be some technical issues, so I will reconnect and just wait for a while.
Hello, am I audible now?
Yes, sir, you are audible, sir.
Yeah, there was some. I don't know what happened. I there was a internet connection problem. So anyway, it is connected now. We should start immediately.
Yes, sir. Dear participants, we have with us Mr. Kaibili Prasad Munda, Research Associate in Institute of Technology, Meghalaya. Uh, sir will just go ahead with this hands-on training session. Sir, please start the session. We may start the
Yeah,
session.
thank you. So whatever the is the slides is visible clearly. Can anyone confirm me?
Yes, sir. It's visible.
Okay. And my body voice is also clear, right?
Yes, yes.
Okay, thank you. So if there is any other again disturbance, please let me know if the voice is breaking some because there is a heavy rain is here, rain is going on. So I think that is the reason the internet connection problem is there. So anyway, there are we have discussed many important aspects of design in the first session regarding the multi-level inverter design and switched capacitor, focusing on switched capacitor multi-level inverter design. And I have also introduced how this is uh, an emerging area of research where you can work on because this is a recent research area where most of the people are working. So you can try to develop a switched capacitor type multi-level inverter because what are the advantages we have seen the boosting ability from a single input source, the voltage balancing ability. You don't have to worry about the capacitor voltage balancing because there is a automatically voltage balancing, self voltage balancing, you can say. And also we have seen that the required number of switches and input sources is very less. You need only single input source that can be used to boost the voltage, and you need reduced number of switches. So not only focusing on the reduced number of switches, you can focus on different other aspects. That is what my point is to highlight what current research is going on, and you can definitely work on it. And where these multi-level inverters are concerned, the main important part is the control aspects. And in the daytime, one of the participants were asking whether what is the control should be, how we should generate the pulses and all this thing. So before we generate the pulses and look after these things, let us know a bit about what are the different control schemes, okay? So that you can easily understand how to go for this MATLAB implementation. So there are two different control schemes generally in the multi-level inverter. What we see, one is the high frequency switching control, one is the fundamental switching control. So you need to understand the basic difference between these two is that high switching frequency control, generally these are generally closed loop control schemes. I'm not saying this fundamental frequency control cannot be closed loop. It can be implemented with closed loop. This NLC and all this thing can be implemented with closed loop. But generally, the selective harmonic elimination type, this is open loop type control scheme, where if you want to connect to the grid and operate and all this thing, generally in that those type of system where we need a closed loop controller in grid connected environment, there high switching frequency control may be preferred. But if you want to operate the system in a standalone mode, and if you don't want a closed loop control of inverter, then you can go for selective harmonic elimination easily, right? So based on this requirement, different types of control schemes have been developed. So what we are doing, basic difference if we know, see in fundamental frequency control till now, whatever I was explaining, let's suppose we will take care of a five, we will take the case of a 5-level inverter where you have two steps on the positive side and you have a zero level, right? And there is a negative level, two steps you are getting. That is why it is called as 5-level output. So you see this 5-level output, this what I have drawn here. Here you can say in one fundamental cycle, this is one fundamental cycle what I have drawn. Then again it will repeat like this. So in one fundamental cycle, if you see, you have one switching per level, right? Means you do not have multiple switchings you are doing here. So that is the reason this is called as fundamental frequency control. or you are operating generally the inverter, most of the switches are operated at fundamental frequency. Whereas high switching frequency means the switches are generally controlled at very higher switching frequency of around, or the carrier switching that is defined based on the carrier frequency, right? So the carrier switching frequency, you might be knowing already about the PWM control, but for multi-level inverter how you will implement that we'll see here. So as you can see, the frequency, the carrier frequency of the PWM signal, that is very high, right? That is of around, let's suppose 2.5 kilohertz, 5 kilohertz, 10 kilohertz. That is in the range of kilohertz. That is not in the range of hertz. So how the output will change? The major thing is that when we see a high switching frequency output, you will have multiple switching in one fundamental cycle itself. Multiple switching, not one switching. So multiple switching means your output will be something like this, where you have multiple switching, like this. You have multiple switching in one cycle. Then here you have multiple switching again in the second level. Okay. Then again, it comes to the first level where you have multiple switching. So what I am trying to say here is that because of the comparison of the carrier and reference signal, you are generating more than one number of one number of pulses or switching pulses in the PWM pulses in one fundamental cycle. So this is this type of waveforms where you can get the you see that is called as high frequency PWM control. So your high frequency PWM control is again divided into, depending on the number of carriers, they are divided into level shifted and phase shifted PWM. So what is this level shifted, phase shifted PWM? If I take the case of this 5 level, where I generally need this type of, these triangular carrier waveforms are taken, and you have a sinusoidal reference, right? So this triangular carrier, based on this, your different types of controllers are defined. So this is called as level shifted PWM control, where you can see these carriers different, because you need multiple number of carrier signals, right? You cannot obtain this type of output with one only carrier signal. So with multiple carrier signal, you can see that they are now level shifted. They are shifted with some amplitude, right? These carrier signals, how they are arranged to produce these pulses, they are arranged in a fashion that they are shifted by some amplitude. So this is called as level shifted simply. Whereas phase shifted means you will see the carriers are arranged in this way. They are shifted in some phase angle, right? You can see they are not level shifted, they are phase shifted, means with some angle these carriers are shifted. So based on that, this is named as phase shifted PWM control. Where this is level shifted one, you can see clearly that the carrier signals are shifted with some amplitude, and here also there is a carrier. So you have a carrier, there is a reference signal. You have a sinusoidal reference, you have a carrier signal, your triangular signal, and the frequency of your triangular signal decide your switching frequency. Whereas your fundamental operating frequency, or what you call the nominal frequency, or the output of the inverter, that is 50 hertz. In India, if I am talking about the Indian context, and you are feeding to the grid of 50 hertz, where the inverter output is of 50 hertz. Are you getting my point? Because you see, this is one fundamental output. If you compare, this will be of 0.02, one full cycle, 0.02 second, right? Because you have 50 hertz means this will be 0.02 second. So your output of inverter is 50 hertz, but the switching is in very high range of frequency, that is in range of kilohertz. And that kilohertz range of frequency, that is due to this carrier signal. Okay. So to bit understand more closely this high frequency and low frequency or fundamental frequency, this fundamental frequency is also called as low frequency PWM control, right? Where we generally, I told you the switches are operated at 50 hertz. So you can clearly see the output of a 7-level inverter. Okay, the output, you just observe the output of a 7-level inverter where there are multiple switchings, right? There are multiple switching in one period itself. That is why you are obtaining this type of output. So this is called as high switching frequency PWM control. So if you see the block diagram of SPWM, the basic sinusoidal PWM control, it is very simple. Basic sinusoidal PWM control consisting of a comparator where you have a reference signal. I told you reference is most of the time. This is sinusoidal PWM control, so reference is always sinusoidal. You have a triangular carrier signal. This is called as carrier, where triangular carriers are arranged in this way. Okay. which are compared to generate the gate pulses. This way you will generate the gate pulses, and that gate pulses will be fed to the switches. Then similarly in your level shifted PWM and phase shifted PWM, these are one type of sinusoidal PWM only. Okay, these are modified type of sinusoidal PWM, you can call it here, because here the triangular carrier signals are arranged in such a way that they are named as level shifted, phase shifted. But that is also the difference is your sinusoidal and the carrier signals are triangular. So, and you have space vector PWM control also, which is one of the very important control aspects people are working on, space vector PWM control. So these are all you can see high switching frequency control schemes. Okay, where there are several advantages, disadvantages of every other switching scheme. But if I compare the fundamental switching frequency or the low switching frequency control scheme with the high switching frequency control scheme, one very important point is that you can understand what is your application, what you want to do. Okay, that needs to be clear. And here you can see that the switching losses, the main important thing is, because you are operating at very high switching frequency, obviously the power losses, what is the major power losses, that are switching loss and conduction losses in a multi-level inverter. So here switching loss will be very higher because of high switching frequency. Whereas in fundamental frequency, you can clearly see the output here, where you have one level clearly per switching, or one switching per level. Okay, per level one switching you are doing here. So in this case, you are getting very low, you are operating at very low frequency, so the power losses majorly switching losses. Okay, there will be no significant switching loss, very low switching loss will be there. Conduction loss will be, no doubt it will be there, but switching loss can be largely reduced by the help of this fundamental frequency output. So my focus here to discuss is that this selective harmonic elimination control, where I have worked on. No doubt we have implemented both the high switching frequency and low frequency control schemes, both in our different works. But here I will tell you about selective harmonic elimination control, which is one of the emerging research area also for you. You may try to understand what is happening here. So in selective harmonic elimination control, okay, before going into that selective harmonic elimination control, I just want to show you how the carrier and reference signals are arranged. You see, your level shifted, these are all level shifted PWM control, these three. If you see this classification, I told you level shifted PWM control is of three types, or three different category it is divided. Level shifted, where carriers are shifted by some amplitude, but why they are named as phased disposition, phase opposition disposition, and alternate phase opposition disposition. Okay, you see, you can see the arrangement. Here there are four carriers.
Sir, your voice is not clearly audible. Participants, kindly wait a while. There might be some network issue. Sir has been disconnected. He will join again. Please wait.
Sir, is the screen visible?
Yes, sir, it's visual.
Yeah, sorry for the interruption, sir. There is a very heavy rainfall, so that is the reason the internet is having some problem. Anyway, I was discussing about this, where I told you about the high switching frequency PWM control phase disposition type, which is having all the carriers are in same phase. Okay, and in phase opposition disposition PWM control, you can see there are two carrier signals are in one phase, other two are in the different phase, right? Which is reverse in opposite direction of these two, or 180 degree phase shifted signals. Whereas your alternate phase of position disposition PWM control, you can see that one carrier is in one phase, the other signal is uh, 180 degree phase shifted. So this is called alternatively they are again shifted by an angle of 180 degree. Alternatively control, right? And similarly, I was telling you that focus, not focusing on high switching frequency, let us focus on something called as SHE, or selective harmonic elimination control. What we are doing here, you understand the concept. Let's take the case of a the screen visible to you all?
Yes, sir, it's visible.
Thank you. So, what to do? There is a still stable internet connection is not there. So whatever we have to do. So as I was telling you, if you consider a 7-level waveform, and for a 7-level waveform where you have one switching per level. Let's suppose you are considering a voltage waveform of this pattern. 7 level means 3 steps will be there. So here, as I was telling you, switching, okay, and 2 and which is alpha 1 and alpha 2 alpha. So what switching calculate the optical, obviously your total absorption will be
The participants kindly be there. Sir is trying, due to network issues, he is unable to join. He will join. So just be there. Thank you.
So we have employed that same rule, whatever I've said. You can see there are three equations relating to alpha 1, alpha 2, alpha 3. How we have developed this equation, this is very basics. I don't want to go through it because in any output of a multi-level inverter can be expressed in Fourier series. 1,000 papers are there on this, you can follow. And for 7-level inverter, I have first equalized one equation with modulation index, because modulation index is the term I told you need to concentrate on. When you vary that modulation index, you need to see what is the harmonics variation. Then another two expression I have taken here relating to, because I can take only three equations, right? Three unknowns are there, alpha 1, alpha 2, alpha 3. Three equations I can take. And as there are three equations I can take, one equation I have already taken with modulation index equalization. So another two equations definitely I need to take for targeting the harmonics. So here I have taken, you can see, third and fifth harmonic. You can ask why I have taken third and fifth, because lowest order harmonic to eliminate is the third. And this is a single phase system what I am talking about. So that is why I have considered third harmonic. Otherwise, if it is a three-page application, third harmonic is need to be avoided. You can consider another order harmonic, fifth and seventh maybe you can consider to eliminate. Clear? But the observation or conclusion from here is, if it is a 7-level output, you can focus on only 2 order of harmonics and you can do only 3 number of equations. You can see one of our review paper last time also I have highlighted. Here I think in this slide we have given somewhere the reference. And you can see these are all high switching frequency PWM control schemes. See the output of the multi-level inverter. This is shown for a 7-level. Again, I am telling you how I am calculating the number of levels. 3 levels on the top, 3 levels down, there is a 0 level. So 7 levels. If there are 3 steps, you can say 2 into 3 plus 1, that is how I calculate. So there are 7 levels at the output. You see the principle of operation is shown in with respect to block diagrams. The level shifted, phase shifted, and the space vector one. So here, obviously, these are all high switching frequency control schemes. Oh, if there is a high switching operation of inverter, that will incur more loss, right? So because of high losses, power losses, the total loss, switching loss, if you calculate in a circuit, that will be higher. If total loss is higher, obviously efficiency of the circuit will reduce, right? But there are different other advantages when you try it your own, the switched capacitor type, what I've introduced just now. When you try it your own, you will definitely get new conclusions from that. The reduction in ripple, then the charging current. About that, I have not discussed here, because that are some of the very advanced things I have not discussed here. That have been highlighted in the papers. If you follow the papers, definitely you can understand. And here, this is a high switching frequency PWM type output, as you can see, right? So these are different PWM control schemes. I will not tell you here, because from the block diagram you cannot understand. We will see in the implementation itself how it can be done. This is again fundamental frequency type switching control. You can see. So in the fundamental frequency type switching control, you can see the selective harmonic elimination. I will explain one in detail, because I personally have worked on selective harmonic elimination control, or different algorithms we have developed here. Nearest level control, one of the switching, another fundamental frequency switching control scheme, which is much easier to implement, no doubt, but you cannot guarantee on harmonic control, because only selective harmonic elimination control, you are selecting third harmonic, fifth harmonic to eliminate, and you are doing the work. So that is different. The nearest level control is something different actually. And different means you cannot have a control exactly on which harmonic you want to eliminate or you want to control, right? But this is also one of the fundamental control scheme. This is space vector control. This is also another control scheme. So these are different types of control scheme we have also discussed in one of our paper. If you see here, to understand the concept first, I have highlighted in the first slide, in the just previous slide, high frequency PWM control scheme means what? Why it is called as higher frequency? That frequency term itself comes from the frequency of these carrier signals, right? So there are multiple carriers here I have taken. You might have been confused with why I am taking this carriers and all. These carriers, and there is one reference, right? I will tell you why I have taken it. This is for generation of a 5-level output. See, if you want to produce a 5-level output, till now what I have discussed like this, a 5 level means there are 2 steps on the top, 0 level, then there are 2 steps on the negative polarity, you can say. So this kind of output is there. So if there are 5 steps in the output, right? Is it that clear? So if 5 steps in the output, let's suppose this is V, this is 2V steps, 5 steps in the output. So you need 4 carriers, 4 carriers, or else you can take 2 carriers also. You can just change the carrier signals, what is that called, the magnitude and all, so that you can do it. So this type of this carrier signal, the triangular signals are called as carrier, and there is one of the reference. The reference, sorry, not reference, the frequency of the carrier signal or the triangular signal, that decides at how much frequency the switching has been done, right? That is the switching frequency. Clear? So here, if you see the difference between this phase disposition, phase opposition disposition, POD, alternate phase opposition disposition, till now, if you see all these publications and papers, you will find there are various papers till now, they are using these 3 control logics. Phase shifted control scheme has been avoided most of the times, because you see there is a multiple number of carrier, very large number of carriers are required in this phase shifted PWM control scheme. No doubt, introduced by some of the researchers in the starting, they've used this control scheme for power balance and all these things in the cascade multi-level inverters, but still they are now, people are avoiding it, because the control scheme is somewhat not easier, or you can say more complex with respect to all these 3 types. These 3 types are almost all similar, but what they have done it here, if you clearly see these 2 carriers on the top here and these 2 carriers on the down, they are all in same phase. That is what phase disposition PWM control scheme, right? All in phase. Clear? And if you see the just a second, the second type, phase opposition disposition, POD, you can see the positive 2 carriers here, they are in a phase. Other 2 carriers here, they are in other phase. So there is a 180-degree phase shift from the carriers. So that is what is POD, phase opposition disposition. There is another one, alternate phase opposition disposition, that is also proposed by another researcher. Here, if you see, each carrier is alternated. See the first carrier and the second carrier, they are in 180-degree phase shift. See the third carrier, the fourth carrier, they are again 180-degree phase shift, right? So all these 4 are alternatively, they are shifted. And you can see, when I say shifted, they are shifted by level, right? The magnitude or level, you can say. They are not shifted by phase, like here in the 4th case. In the 4th case, they are shifted horizontally. What has happened here? Just a second. So here, if you see, they are the carriers are shifted horizontally. Whereas here, if you see in these 3 cases, the carriers are shifted vertically. So this is also otherwise called as, you can say, vertical shifting PWM control scheme. And this can be called as, the phase shifted one can be called as horizontally shifted PWM control scheme. So in all these control schemes, to implement, what you need to do is you need to first generate a reference, that is sinusoidal signal. Then you need to generate some carrier signal generation also. First you try with simulation, I must suggest, because if you really want to develop an hardware, you must try the simulations very clearly. Simulation has to be done properly. If simulation is done, you are halfway done actually. You can do anything then after that. And just trying simulation and haphazardly will not do anything. You need to understand the concept behind the simulation, what it is doing. And you need to test the inverter first in dynamic condition in simulation itself. Then you can go for real-time one. So this reference and the carrier, if you compare, that as sir was also telling, that will give you one term that, as we all of us know, that is, sorry for this writing and all, but that will give you your modulation index, right? The difference and carrier signal amplitude if you compare. So this modulation index variation, you can do the tests by varying modulation index. So not taking too much time on this high frequency PWM, because I will tell you about this fundamental one. This fundamental PWM control scheme. This is also one of our paper. I can say here, you can refer this paper in IEEE International Industry Applications. We have focused on 7-level inverter. So you see, I think I've not shown a 7-level output here. Yes, correct. So this is a fundamental frequency output, right? And you can see this is the grounded signal, 0 signal here. So there are 3 steps on the positive, 3 steps in the negative, and 0 level. So this is producing a 7-level output. So in this 7-level, you can see clearly how many number of instances or switching angles are there. There are 3 switching angles if you want to calculate. Clear? Because if you know these 3 switching angles, you know this is 180 degree or pi. Clear? And this is your 2 pi. And in pi cycle, in the half cycle, you can say this is 90 degree. So all these 3 angles, alpha 1, alpha 2, alpha 3, or theta 1, theta 2, theta, whatever you can call it as, all these 3 angles now are less than 90 degree. That is one of our constraint. See how the control scheme has been developed, that I am telling you. All these 3 switching angles are less than 90 degree. Is that clear? Because this is 180 degree, half is 90 degree. So less than 90 degree is all the 3 switching angles. And one more important thing, you can see the conditions mathematically you can derive. Alpha 1 is less than alpha 2, and alpha 2 is less than alpha 3, and alpha 3 is less than 90 degree, and alpha 1 is more than, you can say, 0 degree. So all this angle, it may be 7 level, 9 level, 19 level, 25 level, any level you design, all these different levels. See, if you go to any number of steps, any number of levels like this, you can consider this halfway is the 90 degree. So all the angles will be within 0 to 90 degree. Is that clear? So within 0 to 90 degree, you have to consider all the angles. That is one of the constraint now. So taking into account that, you need to form a nonlinear equation. Clear? And this nonlinear equation can be solved by they've been developed like many years ago, like you can say 2 decades ago mostly. So people are not now using that Newton-Raphson algorithm because that is not at all easier to implement. One more thing, and Newton-Raphson, there are other problems are there, they require initial guess and all. So these are difficulties in the algorithms. That is why people have developed, leaving this mathematical based approach, people have developed optimization based things. Do you mean by optimization? Here you might have heard, many of us might have heard this algorithms, PSO, the genetic algorithm. These are earlier developed algorithm, I can say, very earlier developed algorithm for selective harmonic elimination. So why we are going for this algorithm? You can ask me why I am going for this algorithm. Where is the equation to solve? What is the algorithm? As I have told you, there are 3 angles, and you want to eliminate, you have an objective here. What is the objective? Now I want to eliminate the harmonic orders. Why I am eliminating only low order harmonics? Because they are dominant in the output voltage of an inverter. The dominant harmonics are odd order harmonics and low order harmonics, not the high order. High order harmonics can be filtered out using a small size filter also, but for a large for the low order harmonics, you need to focus you cannot connect just a filter, inductor filter, to eliminate it. So you need to focus more on that. So you see another point here, because after this mathematical equation, what I will show you, you can understand easily if you understand this one. Here you can see that I have told you there are 3 angles in the 7-level output: alpha 1, alpha 2, alpha 3. There are 3 angles. And if there are 3 angles, how many equations you can form? The nonlinear equation will be 3, right? There are 3 nonlinear equations you can form. And if there are 3 equations to form using 3 unknown variables, how many harmonics you can eliminate, or how many harmonics you can target here? As there are 3 equations, you will have 2 unknown, or sorry, not 2 unknown. You can calculate 2, you can eliminate or target 2 harmonics orders. So it means what? You can target 3rd harmonic, 5th harmonic. 2 order of harmonic you can target to eliminate. Clear? So that way you can proceed here. So we have employed that same rule, whatever I've said. You can see there are 3 equations relating to alpha 1, alpha 2, alpha 3. How we have developed this equation, this is very basics. I don't want to go through it, because in any output of a multi-level inverter can be expressed in Fourier series. 1,000 papers are there on this, you can follow. And for 7-level inverter, I have first equalized one equation with modulation index, because modulation index is the term I told you need to concentrate on. When you vary that modulation index, you need to see what is the harmonics variation. Then another 2 expression I have taken here relating to, because I can take only 3 equations, right? 3 unknowns are there: alpha 1, alpha 2, alpha 3. 3 equations I can take. And as there are 3 equations I can take, one equation I've already taken with modulation index equalization. So another 2 equations definitely I need to take for targeting the harmonics. So here I've taken, you can see, third and fifth harmonic. You can ask why I've taken third and fifth, because lowest order harmonic to eliminate is the third. And this is a single phase system what I am talking about. So that is why I've considered third harmonic. Otherwise, if it is a 3-page application, third harmonic is need to be avoided. You can consider another order harmonic, fifth and seventh maybe you can consider to eliminate. Clear? But the observation or conclusion from here is, if it is a 7-level output, you can focus on only 2 order of harmonics, and you can do only 3 number of equations which are non-linear in nature. You see cos theta 1, cos theta 2, cos theta non-linear in nature. You cannot solve it simply by computation. And also, why you cannot solve it simply by computation? Because you have objective now to eliminate third and fifth. So you need to focus, or you need to develop an objective function, what I have taken here. I will just tell you very simply how I have designed or taken this objective function. Here, this, if you take these values of n and you can put it here, you see. First thing here, I have taken the first term. First term is the fundamental term. That is regulating the fundamental value. Second term is the harmonic. If you put it here, Vn is nothing but the V3, V5. So third harmonic, fifth harmonic, that are taken here. So harmonic components are squared, that are given some importance, and this fundamental component are given much importance. That is why they have taken 4th order, or you can say 4 power, right? The power has been chosen according to importance, first thing. Second thing, this is first term is for fundamental. What do you mean by this fundamental value you want to maintain? You see, I will show you maybe in the output somewhere. Okay, at the end we will see this. Okay, we will discuss that. So this is how the selective harmonic control scheme has been developed, taking into account nonlinear equations, how to solve and all these things. Let us see all this type of this implementation, how it can be done with respect to Arduino. So here we start our Arduino based control implementation. First thing, I will just take you, I will not take time on this controller, because with 700 and 800 rupees you can buy a simple controller, any controller of this Arduino Mega 25, or I can show you here 8 Mega 2560 I have mentioned. 8 Mega is a microcontroller. This is one type of microcontroller, right? And this microcontroller, if you see the pin diagram, you can see there are power pins are there. I'll start with this 3.3 volt, 5 volt power pins are there, so that at any point like this pins are there, you can take here from wires from here, or you can connect wires to these points, all these points. So similarly, power pins are here, and you have analog inputs. Analog inputs means if you have sensor inputs and all, you can fix it to this. See, in PB applications, MPPT is there. In maximum power tracking, there are many other professors, they have already taught us what we need to take VPB, IPB, right? That is clear, I think. VPB, IPB needs to be taken for calculating the maximum power point. So in that case, VPB, IPB need to sense, and you need to give it to analog input pins. Analog pins are, because of that, it is there. You have some PWM pins you can see, and there are that are digital outputs. And here you have here also this side digital outputs, right? So you might be thinking why I'm talking about this controller, because when you buy it immediately, when you start using this hands-on, definitely you will again confuse what you, if you don't know about this controller. So very basic things I'm telling you, and not telling you about microcontroller logics and all. Very basic things what you need to know, I'm telling you that. So this pins here, you can see there are 54 number of input output digital pins are there. Among 54, 15 here on this side PWM output is written. That 15 are taken for PWM pins, and other pins are for your this other pins are for digital outputs. You can also use these digital output pins for the getting the digital output. Digital output means what? That is the PWM pulse. Clear? You can connect this Arduino with a USB connector to your PC or computer directly. I will show you how to connect. You can go for USB protection is also there inside this. Don't worry about it. Another point I want to highlight here, and the serial communication, you know why these communications are there, to communicate with computer or to any sensors. There are communication ports are there. You can see if it is not clear, I cannot do anything here. What a picture what I've taken, you can see TXRX is written, that is transmitter receiver is there. So serial communication you can also what you can do with this Arduino. I have taken only 2560 because this is one of the advantages one, because if you compare with Arduino Uno and Arduino, what is that, Micro, they are all consist of very less number of analog and digital output pins, right? You can see in Arduino Uno maybe there are 14 digital output pins. So 14 pins, and if you want to implement a higher number of switches are there, you need more number of pulses from these points. It is very difficult, right? So you need to buy a controller where you can at least give it to all the switches pulses if you need to give the pulse. Here another point I will show you, that is nothing but your this point here. You see, if it is clear or not, I don't know. In the picture it is read point here it is written L. What is that L? That is nothing but the LED. LED, there is a inbuilt LED on this board that is connected to the pin number 13. There is a pin number 13 here. If you count from 0 here, 0 1 2 3 like that, it is 13 here, and 13 number pin has a inbuilt LED. Why I'm highlighting this one, you will understand after this. So with this, you can go for Arduino controller implementation or programming from, you can download the software from arduino.cc. This arduino.cc software will give you the website will give you the software. You can go for this IDE website, and if you try to download the software, you can write, if you try to write the coding and do this on and try to building means you need to program the controller, if you, because these are all programmable. So if you program it using your control logic, using this software Arduino CC website, if you download and do that programming, that becomes not somewhat easier, because you want to develop the system in simulation, and after the simulation is developed, you want to test it, right? So we will go through MATLAB simulations one. You see, I'll start with MATLAB based implementation here. A simple thing what you can do, all of you today, if you are having 2018 version or I think upper version in 2017, maybe you can try here. I will just check it. I think yes, mine one is 2018 one. So you can go for more upper version than 2018 or 2017. You can, because the recent one is 2020 is there. So we'll try to finish within 10 to 15 minutes. Don't worry, you will understand everything. You see here, this is a Simulink support package for Arduino hardware, where you can download. There is link also I've given here. You can go to File Exchange MATLAB Central. If you directly search here in MATLAB Central, if you search here for Simulink support package for Arduino hardware, search in the search tab. Just click search, you will get it. You just click on download. It will ask you for the permission of your what is that called account. You can open a free account in MATLAB. You can download this. First thing, do that. So if you download this, this will give you the Simulink support package. When you have downloaded, this will integrate with your MATLAB version Simulink. And when you download this, you will now open MATLAB. When you open MATLAB, your 2018 version MATLAB, you see on the top there are Simulink button. I don't want to go through this because I believe, or I assume, all of us have tried with Simulink. You will find definitely a Simulink button. If you click it, what I want to highlight here is you will find this one. You see, it is written Simulink support package for Arduino hardware. After downloading and installation, you will find this Simulink support package for Arduino hardware, right? Up to this is easy. Then what you can proceed is, you just click on this Simulink support package for Arduino. If you click on this, you will find a, what is that called, a help kind of thing. You can see in the Simulink it is available. You see under Simulink support package for Arduino hardware, what is given. There are given some basic model test models. There are given some external models. There are given some closed loop models, some different algorithm how to implement. They have given different things, basic things, only basic things they have given. You can utilize that. So that I want to highlight here. Then the main thing you need to know is about the Simulink library browser. In your Simulink library browser, we all know this also is a very easy. Simulink library browser, where to open, you know. If you open simulation, there, from there only you can open Simulink library browser. So this, up to this we know. Simscape, all these things within that, how you will find the components, the different components. You know about MATLAB. I will tell you about this point here. You see, when you download Simulink support package, what will happen with your library? Automatically, these things will be added. Simulink support package for Arduino hardware. So with that, again, you see there are different this library within library Simulink support package added. This kind of components will automatically appear in simulation, right? Digital input, digital output, analog input, analog output. I told you already how you will utilize these analog pins, digital pins. Then you see I'll focus only on digital input, digital output pins. Digital input, digital output pins will, what it is when you open it, double click, open it, paste it in a new model, Simulink model. When you open, you will see the digital output you focus. It is asking for pin number. What is this pin number? I told you, that is why I've shown you the configuration. 1, 2, 3, the likewise pin numbers are there in the Arduino. You can assign any pin number where you want to get a digital output, PWM output like this. Because this, any controller, even if it is FPGA, even if DSpace, even if it is DSP, these controllers will give you 5-volt output of PWM pulses only. It cannot give you directly a multi-level output. Do not consider that. As we all know, this is controller. This will finally generate only PWM pulse. It cannot generate a output, right? Not a multi-level output. So you need to focus on that. So this digital output digital output, if you know about the component here placed in the Simulink, then what you proceed is the test model. Let us test a simple model here, blinking of LED. Here a simple model has been tested. You see I have taken a sinusoidal, you can tell a block I have taken. And here when you start doing hardware and experimentation, very important thing is your sample time. So sample time, see many important points I'll highlight here. Sample time has been given here, right? 10 samples, 20 samples, you can do it accordingly. So what will that do at the end? I'll tell you. Here at the end, I have taken, you can see the model how it is developed. I have given 1, and here I have given 0 constant things. 1 and 0 is giving means it is just to, you can make it on or you can make it off, right? So you can just blink the LED if you want to test. And how you can just first do the test on LED? I told you that is why in the first slide, there is an inbuilt LED and connected to 13 number pin, right? If you remember here, I told you in the previous slide, to the 13 number pin, there is a LED connected. And because of there is a LED connected to the 13 number pin, if you see here, I have taken here a digital output block, right? And I also told you where to find this digital output block. Clear? So from this digital output block, when you open, I have set to pin number. Just in the previous slide, I have shown you how to set the pin number. When you set the pin number to 13, on 13 pin, this same can be programmed. Now you might be thinking, how this will be programmed? Now you think this is Simulink model. This is done in simulation. Now you think how this will be programmed to the Arduino. How this can be done? That can be done with the 2 upper buttons, what I have highlighted on the red color. 2 red color buttons I have highlighted here. So you see on the top, I have left hand side, I have highlighted here the Simulink. There is a settings symbol, right? This setting symbol says configuration parameter setting. You need to do some configuration parameter setting. Otherwise, you cannot dump this control logic into the Arduino, because that is the main basic thing now left with you. You need to dump the controller. You have developed in Simulink, and very easily almost all of us can design in simulation. How to dump it? Those settings I'll tell you. This setting symbol, there is very important thing that is called as configuration parameter setting. There is another on the right hand side I have highlighted, that is called as build. If you see on the button here, this button is called as build and run. So what this button will do at the end, if you click this build and run, it will build this program logic, whatever developed here. This program logic developed here in this model will be dumped into the controller, right? So that is the final thing. So this configuration parameter setting, what you will do, we'll see it here. Before that, let us see again how I told you how to connect with the PCB. Sorry, not PCB. How to connect with this PC? I'll show you. So I've connected. You can see with the USB cable. You can connect it to your PC, and this is the zoomed in version of your Arduino at Mega
2560 microcontroller. You see the configuration parameter first. When you click on the setting symbol, the configuration parameter settings will open this one. You can go to hardware implementation directly. All the steps I'm highlighting here so that you will not miss a single step to implement or to try it with Arduino Mega first. Click on hardware implementation, open this Arduino Mega 2560, you set it, not open, you need to set it here, the Arduino Mega 2560 board, if it is not automatically set. Most of the time it is not automatically set, you need to set it here. So that is the most important part. If you do not set it here, the hardware board, what you have connected to your PC, simulation program will not dump into the controller. Next thing, you can test it, the target hardware resources. Under this, you will find some additional settings that if you do not do also, it is not a problem. That is why I have not highlighted here. What are the additional settings? I'll tell you, build and run what I told you. Those simple settings you can do. You can set the baud rate of the controller. So that are not required as I told you. First thing, first try, on the first go, you do not need to try on this, okay? See now, when I have run this program just in simulation, how the scope, this scope I have connected here, right? How across this scope I am getting the output. Clearly, I've shown you here the scope outputs with different samples. I told you when different samples are varying, that will affect on the output of the hardware, right? When you implement this on simulation or your, sorry, not in Arduino, how this will affect your hardware output, you can see in a simple video. I'll show it to you here. Let me just choose a here, you can go for this. Yes, so I'll just run this video, you can see the video how this programming, when I'm dumping it at the end, you see the 13 number pin LED, the L is written right here. When where L is written, you can see there the LED is continuously blinking here, right, in the at this point. So why this LED is blinking? Because this program has been dumped into the controller. Very simple test we have first conducted to test whether LED is blinking or not, whether program has been dumped to the controller or not, those things. And 10 samples and 20 samples, with that if you see, the pulses are varying from 0 to 1, but here there are 10 pulses kind of thing, and here there are 5 pulses. So it means what? The blinking speed will increase and decrease. That also you can test with varying the controller samples. So this is how we can test first. So immediately, without wasting time, I will show you 2 more slides here. How to implement switched capacitor type multi-level inverter, because time is too much now. I don't think you can spend more time on this because this is around evening here. You can see the simple circuit diagram I have shown you, and the same circuit, whatever I have explained in detail, that I have implemented in simulation here. You can see I have taken one single source, and I'll show you here what are the sources where I have taken. And there are how many number of switches? Just focus on that. There are 6 switches, 2 switches for generating the levels and 4 switches for generating the output. 6 switches. Logic I have told you, when to on the switch, when to off the switch, I have told you already. That you have understood. Now you will start with that. So this circuit where there are 6 number of switches, that 6 number of switches I have kept it inside this. These are all subsystems, and I will not tell you how to develop a simulation model. I think you all know very much better with that. Pretty much better you can do this. I have done this subsystem where we have placed, if you see S1, S2, these 2 switches S1, S2, right? And there are 4 switches as I told you, T1, T2, T3, T4. Clear? What is there inside this basic unit is the source part. That I'll show you inside what is there. Then the PWM logic, what I've implemented before dumping into the controller, that is there inside the switching pulse. These are all subsystems. And here, this side, it is very simple. Loads are connected, different load combination I've connected. And through the breakers, where R load, RL load, you can vary, and you can see the output across the scopes. I'll show you that. I think it is clear about the model. If it is clear about the model, let us proceed to now the how it is there, what is there inside this. Clear? Circuit diagram is there in your mind now. 6 switches are there. Let us go ahead. So first thing inside this switching pulse, what is there? How we can develop the PWM pulse? One of the participants was asking, tell me first how to develop the switching logic. Yes. Here, switching logic for that. You see, I have connected a clock first. This clock will give me what? Now, whatever simulation time, I think you all know where to give the simulation time, right? If you assign some simulation time on the top of the Simulink model, it will run for that much simulation time. So 0.12 second it is running. That is the clock. Then there is a block here that this is nothing but a MATLAB embedded function block. This block you will find in the Simulink library. You can search it, MATLAB embedded function block, you will find it in the Simulink library. And how many switches are there with you? Just now we have done a simple programming for LED blinking. I told you which pin you need to program, that you need to assign. Clear? I have assigned to 13 number of pin where I have given the PWM pulse. That is why at 13 number of pin, because there is an internal LED that was blinking. So it means that is how you need to do programming. I have taken the Arduino pins here that are all digital output pins. If you sometime refer to this PPT, sometime also you will find out digital output pins. I have also shown you where to assign the pin number. Very simple, right? Digital pins are there where you can assign the pin number. We have assigned the pin number 31, 32, 33 like that up to 5, 6. There are, because there are 6 switches are there. You need to do that. There are how many number of switches, based on that you need to assign. See, when I'm running the simulation, I'm getting the pulses here. Very clearly I'm getting the pulses. Now main thing is that what is there inside this function block then? If you know this, then everything is over. Everything is over if you know this, what is there inside this function block. Because that is what is the logic I have developed here to get the output. If you get this same pulses in the hardware, everything is done. Next, proceed. This is the programming. I told you just now, logic you need to know. I told you at 0 level, which are the switches on. I'm just writing the same code here in terms of 0, 1, that is on and off. 0 is for off, 1 is for on. See, I'll focus on 1 level. In the first step, what we are doing, if you remember, I am turning on S1. So you see, S1 is on, S2 is off. And you are turning on T1, T2. Just focus on the circuit here. T1, T2 on, S1 is on, right? S1 is on for charging the capacitor, T1, T2 on for generating level. So I have just turned on that thing. In the positive half cycle I have given, negative half cycle I have given. Not much time, otherwise I would have explained with you, you all with the switching table also, but I will not spend much time because this is very in detail. I've explained the circuit diagram maybe, so you can just write the coding yourself. But I have just not highlighted one important thing. If you write only this much in the MATLAB, it will not generate or run it. You need to give a first a reference signal. You can write just one line code to take the reference signal sinusoidal. Then from that, I have written this one, right? And after the reference, you can just write these codes and all. You can try it out. You will definitely get the results. So now, main thing is you see here. One more important point. You can see it here. What is, I told you what is there inside this subsystem. Inside this subsystem, these two, basic unit, full circuit. Okay, focus on that. The basic unit is the source, full circuit is the circuit diagram. See, in the circuit diagram first, there are 6 switches. Very clear. 1, 2, these are 4 switches on the load side, and I have 1 diode as in the circuit. Clear? This circuit is now clear, and these 2 points are connected to these 2 points. So that is what is there inside the basic unit. So these 2 points, if you see, I have developed a photovoltaic system at the input side with MPPT controller. There is a boost converter. I think almost all of us know how to develop boost converter in Simulink. Maybe in the BTech level, we almost taught us for how to develop Simulink in the boost converter. But MPPT controller implementation, that you need to focus on. That is not the part of this work, and I will not focus on that. You can develop P&O algorithm, incremental conductance, any algorithm for giving the pulse to this switch of the boost converter. Now you can ask me, because I have told you earlier, this is a switched capacitor type inverter which does not need any additional boost converter, because there is no need of DC-DC converter when you are achieving boosting here, right? Why I have connected again a boost converter here? So there lies the important concept here. I told you, right? When you do an extensive investigation of this work, you will find out the problem with this. So problem is that when you charge and discharge a capacitor suddenly in one cycle, what will happen? The current across this capacitor will rise to a very high value that is called as inrush current for a short period of time in every cycle. So this inrush current will cause the more losses, and also it may damage the capacitor, also some of the switches. So to avoid that, I have in the simulation I have used a boost converter, or else if you don't want to use boost converter, why I've done boost converter, I'll tell you what you can do to avoid this inrush current or high peak currents. You can connect a simple inductor in the charging path. So that is the logic. First, so what I'm thinking, if I just connect an inductor in the charging path, that will no doubt reduce the inrush current to many amperes. To this much you can reduce, no doubt. But the problem is you have to connect an inductor, and in a boost converter, what is the main cost effective part is the inductor, right? So so this inductor anyhow you have to use. So that is why I've developed a boost converter where there is inbuilt inductor is there. You know, in boost converter, inductor, capacitor, diode, and switch is there. So one inductor will act for this purpose, and also with respect to that, another purpose is that you can achieve more boosting. You can say 2 times boosting by this circuit, 2 times boosting almost if we are operating with MPPT with this boost converter, and you can achieve almost 4 times boosting, you can say, with this photovoltaic system. I think it is very much clear here. Now let us move to the results. Now you see, when I'm running in the simulation, you are getting the 5 level output as expected, and you can see the capacitor voltage here. I want to highlight there are 2 capacitors I've connected here. One capacitor is this one, which you need to charge and discharge. What is this capacitor? You see these 2 points across the input is connected to here. So this capacitor can be treated as a DC link capacitor, right? So DC link capacitor output and the output the capacitor which is charging discharging, both are same, nearly 40 volt, if you see. Because I told you, right, input source voltage jitna hoga, accordingly your output across this capacitor will appear. The same output you are getting, and that is why you are getting 5 level output. And I am changing the load. I have told you I have connected R and RL load. When you are running, see the R and RL load change in the current. And because of this change, we have taken harmonic analysis. In the harmonic analysis, you see the harmonics. Generally, in 3 level inverter, the harmonics are almost 35 to 40%, almost. So if it is 40%, I have reduced it to around 18% almost, the output voltage. Current, when it is sinusoidal, after connecting RL load, again I have tested the current THD, almost 3%, which is following the IEEE standard. Clear? So this kind of resultant test you can do. Now, main part, what is left, where is the hardware implementation? Because this is simulation, it is implemented. You have got the pulses like this, what I have shown across the digital pins in the 31, 32, 33 pins. Yes. Now let us move to hardware. Here I have in my laboratory, we have here the different switches, and if you know something there to start implementing the basic with the circuit diagrams, there you will find you need a driver. What is the need of a driver? This TLP250 will do isolation, amplification, because you see this pulses, what you have got is only maximum of 5 volt from the Arduino. Arduino is a maximum operating voltage is also 5 volt. You are getting 5 volt pulse. Can any 5 volt pulse will turn on these switches, these IGBT switches? No. The threshold level of these switches is around 12 volt. Maybe you need to apply that much voltage. Clear? So 12 volt threshold voltage will be given from this driver here. The white color drivers, what you can see. And these are all IGBT switches on board. So again, another important point is that this driver, what is shown here on the left hand side, white color TLP250, how it will get a pulse, because how it will amplify from 5 volt to whatever required voltage of the switch. That amplification or that supply to this driver will be given from another circuit on the right hand side. So that is your supply to the driver, you can say. Here I have used a SMPS kind of configuration. You can say here AC supply is taken, and the load output side, this is giving a constant 12 volt output, nothing else, constant 12 to 15 volt output it is giving this across this capacitor. So that constant voltage, why there are 5 capacitor, you can ask me, I'll also tell you about that, because you can at a time you can give it to 5 number of TLP250 from this point. Are you getting? At a time from this SMPS, you can give it to 5 TLP, 2LP, 250 points. So 5 switches can be at a time fired, or at a time can be given supply to these drivers. Now this is our developed setup here. From the top view, side view, you can see everything. I have used a DSP controller. What I have explained you till now about a Arduino controller, which is the first initial starting stage. You can try it with Arduino. Then you can go for this DSpace, DSP and all I told you. You can see there are nonlinear load we have connected. We have connected the switches with heatsink. That is the same switch configuration what I've shown you. There is only difference here is that there are some switch heatsinks are there to dissipate the heat. And this circuit I've told you supply to the driver, it is giving here. Okay. Then we have also connected the load combination, R load, RL load. There are also, we have programmable DC supply in laboratory. We have current probes, you know, might be knowing. There are MPPT controllers. Here you can see there is an MPPT controller developed with Arduino controller. And we have also solar simulator in our laboratory. Solar simulator is giving the required, if you do not have a PV panel, right? Because PV panel controlling shading pattern and all, it is very difficult. The solar simulator, if I take again, if I start explaining, it will take another 1 hour. So I'm not going deep inside the solar simulators, how to use it. Maybe this you can buy it in your institute and you can try it. And if you want to know more information, you can just discuss. We'll discuss later on. You see here at the end, I want to just show you with both fundamental frequency control scheme and high switching frequency control scheme, the output we have obtained across the oscilloscope. This is the scope coder. The high power, you can say high quality results we have obtained here with difference in the output voltage. The yellow color output, you can see how it is getting the output of fundamental and high switching frequency. Clear? So this is how we have tested our inverters. Again, I want to highlight you one important point. You can go through all these papers. If you have any doubt or you can any question, queries, we must discuss in detail.
Excuse me, sir. Am I audible?
Now, so
sir, am I audible?
Yes, sir, it is audible, sir.
Okay, thank you, sir. So I'm very sorry for the disturbance caused here due to this rainfall, heavy rainfall. So I discussed with Biresh sir to play the video, and so
Yes, sir,
this
no
was
problem,
a yeah, some of the things that are missed. That is, I was about to discuss about MPPT control and implementation of MPPT control also in the Simulink and hardware platform. But anyway, the important parts to start with the multi-level inverter integration and how to develop in your hardware platform. To start initially, I have given the full clear picture. I will also share with you all the slides so that you can get all the links to download the support package and how to install, how to work on that. Every stepwise I have given the idea in the slides, and I think you can get the clear picture out of it. If you have any doubt, so quickly you can ask me. I don't know when the internet connection will again stop. I am sorry about that. So if any doubts are there, I'll be happy to answer.
Dear participants, any queries you could ask?
Good afternoon, sir. I have the
Good
same
afternoon.
question as I was asking during the morning session. You had shown that while using the Arduino, we can use that embedded MATLAB function and we can generate the pulses and all those things. But
Yes,
if
yes.
we are not using the Arduino and we are doing it in the software only, MATLAB software. So if I'm having more than one switches, maybe it is for a converter or an inverter. My doubt is how to generate the pulses so that I can control all the switches. Like if I'm having two switches,
Yes, yes.
then how to control both the switches simultaneously?
Yeah, that is what I think I have shown here in the, if one point of time, if you have observed, I
Yes,
have
sir.
shown you one of the MATLAB programming function block. So
Yes,
there,
sir. Hmm.
yeah, you can write the program logic for the both the switches,
Okay.
and then you can obviously control it. If you want to
Sir,
develop only on Simulink, you are telling.
yes, sir. So the output, the Y of the MATLAB embedded function that you had given to different Arduino pins,
Yeah,
as you
at
have
this
shown
point
there.
I have
So,
given two different Arduino pins,
right.
and what you can do, you can give it to your switches in the Simulink model. Your
Huh.
switches will be there, so you can directly give those output points to the Simulink switches.
So here we can generate different types. Means suppose I want to use different, let's say four switches are there. Two
Yeah.
simultaneously it will switch on and two simultaneously it will switch off. So that program
Yes.
had to be written in that embedded MATLAB function block.
Yes. 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 Obviously. Yes.
Okay, okay, sir. Thank you, sir.
Yeah. Yeah. I think I have shown that programming also how to write, and let me just share the screen. Uh, Yeah, if you see here on here, I have told you how to write the switches, which 0 1 indicates here which are on and which are off. So you
Yes.
can on switch on and off any point of time, whatever the switches you need.
Mhm.
Let's suppose it is a multi-level inverter or three-level inverter or any of the inverter. You can write the logic behind the switches, which are needs to be turned off at what point of time. You can write accordingly. And here Y is actually generating the pulses, required switching pulses of the switches, and that can be given to the switch. Here I have also connected. I have also given those output to the switch. If you see here, I am giving the output in the Simulink model itself to the switch.
Mhm.
And out of this Simulink model, you can take only this digital output or the pulses from the controller. Then that can be used for your hardware development also.
Okay.
Yeah, thank you. Any other queries? So if there
Yes,
are no
yes, sir.
queries,
I do not think there are any queries right now.
okay, no
Thank you,
problems.
sir. Both the sessions were quite nice and interesting. There might be some little bit of network issues in the second session, but still we think it's been managed. And thank you, sir. And in your future also, we'll love to hear from you and regarding your
Thank you so
new
much. And
research and findings as well. Thanks.
yeah,
Thank you so much.
thank you so much.
Now, esteemed dignitaries and dear participants, at the end of this 2 days e-workshop with hands-on training session on advanced MATLAB tools and Simulink for power system applications, I would like to propose a vote of thanks to all the people who have been instrumental to this success. I would like to thank Dr. Sandeep Bose, Director, Silicon Institute of Technology, Sambalpur, for his guidance and inspiration for this conduction of this event. I'd like to thank Professor Dr. Inakshi Das, Dean, Silicon Institute of Technology, Sambalpur, for her continuous encouragement and moral support. I accord my sincere gratitude to our resource persons, namely Professor Dr. Siddharth Panda of DSS University of Technology, Bulla, Dr. Amit Kumar from Thapar Institute of Engineering and Technology, Patiala, Punjab, Mr. Kaivalya Prasad Panda, Research Associate, NIT Meghalaya, for taking time out of their busy schedule to grace this online workshop with their kindly presence. as well as sharing their knowledge and research outcomes. I thank all my dear colleagues and the technical team who have significantly contributed in diverse roles and capacities to organize this national level online workshop. Most importantly, I extend my heartfelt thanks to all the dear participants for being with us over the last 2 days and for their active participation and interactions. Thank you all. Have a nice day. All the dear participants, please fill the feedback form. I've already attached over there. Let me send that again. And all the documents and the PPTs, once I will collect that from the speakers, I will mail that to you. And again, all the links of this and the video recording of this, all the 4 sessions, I will again mail that to you in your corresponding email IDs. And those participants who have attended all the 4 sessions and submitted the feedback forms will be provided as certificates, most likely within 7 days. So thank you. Please kindly fill the feedback form. Have a nice day.